There we go. Recording is started. So welcome everyone to the Engineering Challenge webinar for Moon and Mars. Our speaker today will be Mark Abotossaway again. And just to quickly go into the obligatory contact slide. So everyone, you guys need, take snapshots, screenshots, or pictures in case you guys need to harass us with any emails. Otherwise, I think I will hand it over to Mark and let him run wild.
Yeah, hey everyone. Good afternoon. It should be afternoon everywhere, right? Who got on the call? Let's see. All right. Welcome to the Challenge 2024 Challenge webinar. So in this webinar, we hope to give you kind of some answers or an overview of the challenge as outlined in the handbook this year, and give you a little more detail and be available for questions. So today's presentation, I forgot to put the vehicle. We'll talk about the payload requirements, and those are the points listed as outlined in the handbook. We'll talk about the payload chassis. We'll try and be general. I'm going to try and talk, both the Moon and Mars are very similar. So I'm going to try and just be general enough where, it's going to both apply to Moon and Mars, where it's not applicable to one or the other. Hopefully it's evident, or if it's not, let me know in the questions or on the screen or however. I know we have both Moon and Mars challenge teams here. Electronics. So those are kind of the electronics for Mars. Some of them are applicable to Moon. Integration is the same for Moon and Mars. Deployment is the same, basically the same for Moon and Mars. Control is specifically for Mars. And then we'll also talk about, I think the last slide is the vehicle requirements, which should be identical for Moon and Mars, almost identical. Next. And then also feel free to jump in with any questions along the way. Yeah, we should be good for time. I don't think there's much here to review. So if there are any questions about a specific slide or statement, or we can come back at the end. The chassis. So talking about the challenge payload chassis. So this year, right, Moon and Mars have to develop a rover or a deployable chassis. So for Mars, right, it's a drone. And it says teams must fabricate a drone chassis. But for Moon, it's also a chassis. It's just not a flyable chassis. It's kind of like a lander chassis, like you can see in the middle there. And I guess you guys can't see my cursor. That's only showing to me. But the middle image is kind of a lander, representative of a lander type vehicle. It's just going to fall on a parachute. Thanks, Rob. Right. Teams must first design a chassis. So your proposal coming up here, I think in 4 weeks, your proposals are due. Your proposal should present at least 2 variations of a chassis. So if you're in the Moon Challenge, right, think of like 2 different variations or 2 different chassis types you want. And then same with drone as well. Think of 2 unique chassis types and present those to us in your proposal. And then a typical chassis, of course, will have a body, which houses the electronics. So you can see in the 3 images, right, whether it's a powered drone or just a falling lander, there's a body. And then there's also arms. So in the Mars Challenge, right, we'll call those arms where the rotors and the motors go. On the Moon Challenge, those are legs, very similar to the arms in the Mars Challenge, allow for stable landing. And then landing gear. And, this isn't like an airplane like you think of typical landing gear, just allows for stable landing. So you can see in the drone images there, there's kind of just pegs in the 4 corners, and that's kind of their landing gear. So when it touches down on the ground, the body's not necessarily touching the ground or wherever it's landing. So just keeping those in mind for the Mars guys. You still need kind of legs, even though you have arms for your control. You still need something to kind of touch down on the ground with. Next. And then, continuing along the lines of the fabricating the drone chassis. Chassis design may be based off an existing COTS chassis. I think we had this question in the last webinar. So you could design from scratch. Maybe your school, or maybe you've got some drone experience, or you've got some payload experience, and you could design something completely from scratch. So you're designing the size and shape of the body, and maybe you're designing the diameter and thickness of the legs and the length of the legs or the arms. Or you could just design off a COTS chassis. So you could go out and say, hey, I'm going to Google all the different COTS drones there are out there and look, and you'll see some similarities and some differences. And you're going to say, hey, we like this one. We like this drone. We're going to basically build this drone from scratch. So, and maybe that entails, maybe, if you have the budget, you're going to look at your budget and always, update those in proposal. Maybe you go and buy the drone, right? Just as a comparison, something to build to. You can't use the COTS chassis in your competition drone. If COTS chassis parts are used, points will be deducted. However, worst case scenario, maybe you do want to have a COTS chassis on hand. So say you're fabricating arms and it's, March or April and it's 2 weeks out from competition and you just can't fabricate the arms properly, or they keep failing in tests or something, right? It's better to go with a COTS component and have a successful flight than it is to go with a fabricated component and be uncertain of its performance. So we'll take that into consideration. So try and design as much as possible and fabricate as much as possible. But it's up to each team if they want to go and start, if they want to buy a COTS chassis or a COTS. And COTS, of course, stands for commercial off the shelf. So it's kind of just a ready-made component that you pull off the shelf or you buy from somewhere, and there's nothing really. It's plug and play, nothing really to design or test with those. COTS have already been tested and designed for you. Any unique features or designs would need approval. So again, that's why we tell you in your proposal, tell us exactly what you're going to do or how you plan to do it. Right? I mean, I don't know what you guys are thinking. You guys could be like, hey, we want to do a single spike and we want 10 different things coming off of it. Let us know what the design is ahead of time, and myself and Frank and our judges will review it. And if there's any issues with either the engineering, the structure, which is kind of my area of expertise, or any issues with just the safety aspect as far as flying or having a component like that fall at Bong Park, Frank will also have input on that as well. So then chassis material, you can use any material you want. You can 3D print your entire, body and arms and everything. You can 3D print your moon lander. You can use composite, so you can use carbon fiber. I know last year's teams, that was the challenge, really. You guys got a lot of experience into fabricating parts, whether they were 3D printed or composite. And you could also use metal. Don't make the whole thing out of metal because it's going to be too heavy or too much. But you can use small metal components if you need to for the structural strength. If you have machining capability and you need something rather unique. Any other exotic materials would need approval for as far as the challenge payload chassis goes. So again, submit your materials. Be clear in your proposal what kind of material you plan to use for your challenge payloads. Next. Additional chassis requirements. So the chassis must be retractable. And this goes for both Moon and Mars. So I've included some images there of retractable drones. So you can see they kind of retract in different orientations. There's one that kind of, I think the front arms on that top one kind of swing. They pivot around a ball, like a ball joint, where the aft arms actually pivot just around a axis. I think the middle image, actually, both of them just pivot around an axis and they kind of overlap on top of each other. So it's kind of up to the teams to figure out which method do we want to be able to retract things in, which orientation do we want to be able to retract it in. And then not only that, how do we want to deploy it, right? How is it mechanically deployed? Is it a spring? Is it a motor? What type of spring? Is it linear motion you could be using to extend the arms of that? And then making sure once they're extended, they lock into place. Like, how do you ensure that it's actually extended and locked? Like, it's not going to move around, right? Especially with the drones, you don't want one of your arms being kind of loose to move, because that's really going to throw your drone flight off of the stability, right? And it's the same thing, even though the pictures aren't there, it's the same thing with your moon landers, right? You want your landers' legs to fold in, however you're planning to fold them in, and then you want them to lock out. Once it comes out of the rocket, it has to be able to lock in a locked out configuration. And then use CAD models for spatial integration. So that's one thing that I see kind of teams running into an issue is, a team's going to go and design something, or they're going to go build something, and then later on they're going to find out it doesn't fit into the tube, or doesn't, it's too big, or it interferes, or something happens, right? So I'm going to suggest that especially the Mars teams use a lot of CAD modeling. Know your dimensions exactly. Build to your dimensions, right? And you're constrained by the size of that tube, and we'll talk about that when we get to vehicle requirements. But in your CAD, you should have a design space, which is your circle and your volume, and everything you design should fit inside of that. And then you need to think also of your deployment, which we'll talk about again in a couple later slides. So use CAD modeling. You'll have to be able to model these your payloads and put them on the computer. Make sure everything fits and moves properly. The chassis must also have the ability to attach and release a drone parachute. So this is something that's not on a COTS drone or a COTS lander, for example, right? It's an additional requirement that we have for safe deployment and operation at Richard Bong Rec Park in Wisconsin. So you're going to attach something to the top of each of those drones, like kind of in the center. Maybe find the CG of the drone, right? And you're going to have a parachute coming off of that center of gravity. And I think we talk more about the drone deployment here in a couple of slides. Next. Size, volume, and weight are your design drivers, basically. So your size, you're restricted to an 8-inch cross section, and that's the folded size, right? So you need to be able to reduce your drone down to an 8-inch circular cross section. Of course, drones, when you fold them, right, they're not circular. It's going to be some sort of rectangular. So it's going to be a rectangle that's inscribed in a circle. And then the rest of the volume you're going to fill with however you deploy, if you're using a sabot or whatever it is using to deploy that. The length is not restricted, so you can design your payloads, your challenge payloads or rovers or landers to be however long you want them to be. I think there's actually an open configuration requirement in the handbook of, yeah, there it is. The payload should be larger than 16 by 16 square. So those arms, you can see in that top drone, for example, between Rob, can you draw a straight line between the arms on the propellers? Yeah. So between that and that should be 16 inches all the way around when it's fully opened, or greater. So at least 16, if not greater. And then your volume is restricted, of course, to the cylinder of that 8-inch circle, and then however long you want to make that volume, right? The cylinder, so you can get your payload inside of there. And then your weight is restricted to between 1 and 3 pounds. I think that's applicable to both Moon and Mars. So that gives you a little bit of wiggle room as far as components or material, right? You can be a little heavier, a little lighter. And then you're going to make your component selections based on that. So if you're in the upper end of that range, if you're a 3-pound rocket or a 3-pound payload, you're probably going to have your motors are going to be a little more powerful, probably, because you want a little more control. If you're a 1-pound rocket, your motors are probably a little smaller, a little cheaper. So maybe you want to aim for the 1 pound. If you come in under, you need to add ballast to at least get to the 1 pound. And then ballast could be anything, right? It could be anything metal, a bag of sand, or anything you want to stick on there to add weight. CG is also important. So pay attention to that in your design. You kind of want your CG to be, as most of the drones you can see in the images are, right? You want your CG to be in the middle of that X, right? So you don't want all your components sitting forward or aft or left or right. You also want your CG to be kind of low, like lower than the 4 rotors, right? So make sure your CD is not high, sitting above the rotors. Make sure it's low as possible, really. And that allows for stable flight when the drone comes out or the drone goes into a tilt maneuver or things like that. It's able to fly in a stable configuration. So size, volume, and weight. So keep all 3 of those in mind. Component selection will also drive chassis design. So and we'll talk more here about component selection in a minute, but the size of your chassis, the diameter, the length, the shape, it all depends on which components you select. Maybe you got a big camera, maybe you got a small camera, maybe your camera is movable on a gimbal, or maybe it's fixed. And that'll kind of intertwine with your chassis. So don't constrain one, and then don't just decide, hey, we're going to build a rectangle and then match everything else. Do the component selection and the chassis design in parallel. So they should be kind of iterative. Make a chassis selection first, make your component selections, change your chassis to match your component selections, and repeat the process. Next. And then payload electronics. So this is for the Mars challenge. I guess I didn't identify. The last 2 are basically for the Moon challenge. So for Mars, we want a controllable drone. It has to have a radio transmitter receiver. You have to have electric motors and propellers. And then you have to have a GPS system and camera. For Moon, you just have to have a GPS system and a camera. And then the camera on the drone is a live feed. So you can, you need to be able to watch your drone in flight. The camera on the Moon is not a live feed. It can be if you want, if you have the budget and you want to do a live feed on your lander. But it could just be a GoPro, some system, right, that's just recording footage and you capture it later. Next. So drilling down a little more detail, radio transmitter receivers, right? You can buy them separately. You can mix and match, which controller you want, which transmitter, or you can use a COTS component. So we mentioned earlier in the chassis design, right? Some teams may be looking to just go out and buy a COTS drone, right, for some chassis ideas or to reverse engineer a chassis. If you go out and buy a COTS drone, we got nothing wrong. There's no objection with you just stripping those electronics. So you could pull everything off the COTS drone and say, hey, I'm going to pull this camera off. I'm going to pull this controller off, this GPS. I'm going to use all of these electronics off this COTS drone and just repackage them into my fabricated chassis. So that's what that means there. Can strip or use COTS components. And then cost and performance basically are your selection drivers for your payload electronics. So you want to keep your cost down. There's a requirement for the cost of your payload, and then performance, right? We all want the high-end fancy stuff that does a million different things, but just for our challenge, maybe a lower-end controller is sufficient, right? Maybe you don't need the controller there in the middle with the screen attached. Maybe you don't need the FPV goggles. Right? Maybe just having your cell phone attached to a controller is good enough, and that gets the job done, and that keeps your cost down. So we'll also be reviewing your cost in your budgets. Next. Motors and propellers, of course, like I mentioned earlier, if you have a heavier payload, you're going to require more power from your motors. Again, you can just buy them separately. You can wait till almost the very end and say, hey, we're just going to add on these motors or try different motors. So make sure you understand the motor performance and how they work with the propellers. Worst thing to happen, you don't want underpowered motors, right? You don't want your motors, you don't want your drone struggling to gain lift or control, for example, right? But you also don't want it to be, you don't need to build a Ferrari either. It doesn't need to be super maneuverable and quick. It's kind of all about the balance of cost and performance, which are your selection drivers. So make sure you get the right power and the right size of motors and propellers. Next. Camera transmitter receivers. Again, you can just buy them separately. There's lots of hobby shops out there that you can look for cameras and receivers. RC cameras, things like that. Or you can strip and use COTS components. So if you're going to go out and just buy a COTS drone and pull those components off and use that camera and receiver, you are allowed to do that. So go ahead and do that. Again, cost performance are your selection drivers. So you're trying to keep your costs down. So again, you don't need the super high end, 4K, whatever. You just need something that gets the job done. You need something reliable. Something that's reliable, especially. So then in the images there too, you can see some of the radio controllers include camera screens. So we saw in an earlier slide, right? One of the controllers has a screen right on it where the camera feed comes to the screen. I think that's a DJI controller. So the camera and all the control are fed into one box, and you can watch the video as you control it. Some of the high-end stuff, right? You can see the goggles in the upper right image, right? That's kind of a higher end type camera receiver. And then the lower end, the cheap end stuff, right? Just your cell phone. It's funny, the blue screen doesn't let you see my cell phone. But cell phone. A lot of the controllers, you just attach your cell phone right to it, and it uses like a Bluetooth or a Wi-Fi to transmit the video to the cell phone, and then you can control your payload just by watching the video of what's going on your camera or on your cell phone. Sorry. So make sure to balance all that. Let us know your selections. Of course, there's a GoPro camera for the Moon guys. If you're feeling up to it, go ahead and do a fancy camera. You can get a live feed. Otherwise, just go with a GoPro, something on board that rides down on your payload. One of the benefits for the Moon guys, if you have the live feed camera, it might help with recovery because out of Wisconsin, there's a lot of tall grass. Who knows where your payload's coming in? There's been times we can't find stuff out in the tall grass. So if you have a live feed, it kind of helps you get a better idea maybe where you landed when you're going out to recover your payloads, for example. And we still haven't figured it out, but we'll have a number of drones on site apparently. So maybe we can also use those to help recover everyone's components at the end of the day. Next. Payload integration. Wish I had some more images for this. So this just kind of refers to installing your challenge payload inside your rocket. And it also refers to ensuring the payload is ready for deployment and control. So that's what we talk about. That's what we mean when we talk about integration. The vehicle and payload should use a sabot or a piston to protect the payload during flight. So you're going to build this drone or this lander, right? At some point, it has to go inside the tube. So we need you to think about not only just, when you stuff it in the tube, right? How does it get out of the tube? So maybe, your legs or your arms, maybe they have a roller on it, right? So maybe you want like zero friction, or you want to try and reduce the friction so it doesn't catch when it comes out. Maybe you want to have a piston inside the tube. And then the payload just simply fits inside the piston. And then when you drive the whole thing out, you're basically pushing the piston, which is pushing the payload. And that also reduces friction. That'll ensure that it comes out properly. Another thing too is, whatever you're using to eject the payload, whatever's on the other end, if it's a nose cone, for example, you don't want to jam the payload into the nose cone. So you need to think about what kind of interface is on the other end, right? And can this payload also take the compression load? Or are we going to have something wrapped around it that's pushing the whole thing out? Are we going to use the payload itself to push on the other object that we're deploying? So think of those things in payload integration. Again, you may want to throw out some ideas how you're going to do that in your proposal, and then narrow those down by PDR and CDR and make those built and happen. Next. So that's the mechanical integration. Payload deployment. So again, in the requirements, your payload needs to deploy at apogee. Moon and Mars have different apogees. And then you need an electronic device basically for your deployment. So it's kind of similar to how you deploy your parachutes. but you cannot use a parachute deployment as a simultaneous deployment of your payload. So I think there's been questions already, and I can imagine your brains are thinking, well, if I gotta use an ejection charge to push the parachute, why not just put the payload on the other side of the parachute and push both at the same time? And we don't want that. We are kind of making the requirements such that you cannot use a parachute ejection charge to push both a parachute and a payload. The payload has to have its own ejection charge or whatever means of pushing out, and it has to have its own electronics to trigger that event. So you're going to need, your drogue parachute needs electronics, your main parachute needs electronics. You're going to need a third set of electronics for the payload to ensure that event happens at the required time. And then this device, whatever it is, right? If it's an altimeter or a timer or something like that, it can sit either in the rocket or on the payload, right? So you could, maybe it rides with the payload, and whatever happens, it goes with it, or maybe it just sits inside the rocket, and maybe there's a bulkhead or something, you sit in there, and that's what you're pushing off of, and it stays on board the rocket after that deployment. So you need to think about, do I need a bulkhead on the back of my airframe separating the parachute from the payload, and then how I'm going to trigger that event as well. Mechanical means for deployment can be energetics, which is preferable. You can use black powder or Pyrodex. You could use CO2 if you need to. There's rocketry CO2 canisters that also, you're basically just inflating the volume, right, with pressure. The pressure is going to push off whatever's on the other end, and then everything's going to come out. Or mechanical means. And then all components, whether it's the nose cone, the sabot, the piston, anything that we mentioned, everything must be either tethered to the rocket or have its own parachute. So, for example, if your payload is pushing the nose cone off, the nose cone either has to be tethered to the tube, or the nose cone itself has to have its own parachute when it's descending. So don't forget about that. Include those in your design plans, in your reports. Next. At Apogee, the payload must deploy, right? So we're saying the payload must deploy with a drogue parachute upon open on deployment. So again, what's going to happen is for both Moon and Mars, at Apogee, rocket rolls over, ejection event or event goes off, payload comes out, and as soon as payload comes out, it's got to have a parachute on it. So there's no like a secondary triggering, right? It's just kind of, you're going to fold up this parachute and put it in the tube at the same time you're putting the payload in the tube. And just by the action of it coming out at apogee, that parachute will open up. And that'll kind of retard the descent rate of your payload. And then your payloads all descend at, they open at 2,000 or 2,500, and they're all going to descend down to about, 500 feet, at which point you'll control your drone. Except for the Moon guys, right? Moon teams will not release the parachute. Mars guys, however, you'll have a mechanical device to release the parachute, and also electronic device to trigger that release. Next. I think I talk about this a little more on the next one. Okay, so no. So going back, you can go back or we can stay. So just to be clear, the parachute that comes out at apogee, it stays fixed to the drone, on the Mars drone. It also needs to release at 500 feet. So that's what this line here says, and I believe it's in the requirements. And we want that parachute to release, because we don't want that parachute to tangle in the propellers when you start to power on your drone, right? So basically, the parachute has to just fall away. The drone's going to fall maybe 100 feet or whatever it is, and then you're going to power up your propellers when the parachute's gone away, or sufficient distance away, and that's why we need the release. So it should just be a simple device, whether you're using a computer, Raspberry Pi, Arduino, something that's just, maybe there's a hook that your parachute attaches to, and then at a certain altitude or 500 feet, you trigger the hook to release, and it pulls back, retracts, and your parachute just falls away. So that's what we want there, just for the Mars teams. Next. So now your parachute's gone away. Your payload's still falling. It's 400 feet AGL, and now your pilot must be prepared for flight. So your pilot's going to be watching everything from 2,000 feet, and this is for Mars guys. Ensure the payload is ready for flight. So you should be doing power up and whatever you need to do at 2,000 feet. You should be, ensuring that your drone's, sensing its position. It knows its GPS position. It's got power. It's powered up. You've got visual, so you should be able to see camera footage, or you see what the drone sees at 2,000 feet, all the way down to 400. So at 400, as soon as that parachute goes, you should be able to just power up your rotors, power up your motors and your propellers, and be good to go, ready for flight. At or above 400 feet AGL. And then once you're powered up and flying, maybe you'll stop into a hover at 400 feet. And then your pilot will fly the drone by line of sight or using the camera assistance to the landing zone. And we'll have the landing zone scouted out or marked out on launch weekend. We'll give you more information about that in the launch webinar. Next. And then finally, rocket vehicle requirements. So these requirements are specific to the challenge. Don't confuse this saying that, of course, there's a ton of other challenge or requirements that we have for the vehicle. It has to have 2 altimeters. It has to use a motor eject. This is just specifically for the challenge I'm going to talk about here. The rocket vehicle must use a 7.5 or 8-inch diameter airframe for the payload section. The length of that airframe will vary depending on your payload. So you're allowed to vary the length. So if you want a really big payload, you need it to be long, you're going to make it longer. If you can fold it up small enough or something, you can fold it up and be shorter. Teams may fabricate their airframe if desired. So you don't have to go out and, you can go buy COTS, you can go buy some phenolic or whatever it is, or, carbon fiber or whatever you need to buy. If you're comfortable fabricating, as based on last year's challenges, you can also fabricate your airframes. And then teams may transition to smaller diameter airframe for the booster to save weight and cost. So if you look at the image there, the image kind of shows a transition. This rocket's kind of exactly maybe what we're looking for. That upper section you see just under the nose cone, the maroon section, is an 8-inch section. So that's exactly kind of the payload section that we want you guys to put your drones in. It may not be as long. Maybe it'll be a little shorter than shown in the picture. And then the gold section in the middle is a transition. It's basically coming back down to a smaller diameter. And then the section there that he's holding, that's a 6-inch diameter airframe. So he steps, this rocket stepped down from a bigger diameter to a smaller diameter. You don't necessarily have to do that. If you want to run a full 8-inch section all the way, and then you can go ahead and run a full 8-inch section. Maybe your rocket will just be a little shorter and squatter. But again, it's cost, weight, performance. You're looking at all those features. And maybe if your weight's too much, you need to get weight out. Maybe this is an option you need to look at. This will save weight. And then make sure you satisfy your performance requirements with whatever selections you guys make. So you should be simulating from day one. Simulate, and simulate. And next, I believe that's all we got. Turn it over to questions.
Yeah, just to iterate on Mark's comment about releasing the parachute from the drone, we're allowing that 100-foot buffer because some of the altimeters could be off by 10%, plus or minus. We want to make sure that you clear that parachute from your drone and make sure it's at that altitude at 500 feet as you release the parachute. So the drone has time to think and turn on before it gets to that 400 feet. So its orientation is correct. That's one of our safety concerns.
No questions. Come on now.
And yeah, right. Also, if you have a problem with parachute space containment on certain items on your rocket. There's a company out there called Top Flight Rocketry. They make thin mill parachutes. It's a parachute. It works great. It makes parachutes for drones and falconry and rocketry and high power rocketry. You can order thin mill or any kind of fancy chute you want, and it is affordable.
Well, there's a plug if I never heard one.
Right?
Frank gets $5 for every one of those sold. Frank gets $5.
No, my son makes them. I have nothing to do with his company. This is that it's affordable. It's a parachute. It's just a parachute. It doesn't have to be fancy. It works very well. I use them. I use other chutes, and they work comparable as the top end ones.
Come
I
on,
have a
guys.
question.
There we go.
You mentioned, I think also in the rules, it states that you have to use the a motor with like a delay charge at the top after it burns out for the at least redundant for the main. We can't just use like a standard like avionics to deploy a black powder charge and then a redundant black powder charge. We have to use a motor with a delay on it.
Yeah, it's consider it like a tertiary. It's like a third redundant or triply redundant charge. And that's just based on safety issues that we've experienced before.
Okay.
Yeah, you can use both. We're using both the motor ejection and electronics, both.
Okay. And is this is it for the drogue at apogee or the main? Can you use it, or does it have to?
It's at apogee for the drogue.
Gotcha. Thank you.
Yeah, we'll make sure that you got the right parachute in the right spot in your reviews. Any other questions? Anything you guys thinking that you want to propose or run by us, or you don't want to spill all your secrets to the other teams, or what?
On the moon challenge, do not have like a blade, a sword, or something at the bottom of your lander so it sticks. You got to have the landing legs, please.
Come on, Helen. Where's all your questions?
Right?
Okay. Yeah, I do have a question. So, okay, we're doing the moon challenge, all right? So, you said that the nose cone needs to be either tethered to the rocket or coming down on its own parachute, right?
Mm-hmm.
Can the nose cone be tethered to the payload?
I guess I'd never thought about that.
Would that contribute to the weight of the payload then?
Yeah, I'm more leaning towards no. I don't want the nose cone tethered to the payload.
Okay.
I see issues with that. So I'm going to say no offhand, Helen. Thanks for pointing that out. I'm going to say no at this point.
Yeah. Okay. Okay. So, but the thing is that the nose cone can be deployed by itself with its own parachute, though. We can count down separately, right?
Yeah. We've done that before in the past where we've had sections kind of separate in flight and they've kind of just descended on their own.
And the thing is that at apogee, when the payload is ejected from the rocket, I think the nose cone can just slide out, and the payload can just slide out as well too, right?
Yeah.
Okay. Yeah. Okay. That's great. Yeah. Thank you very much.
Yeah, no problem, Helen.
I wouldn't call it our trade secret, but that's one of our evil plans.
Well, I'm looking at it too. You know, if you have a recovery strap hanging out and you have another free-form object that wants to get out and get away, you know, I'm not going to give any more clues what might happen.
Okay, I have a question. So
I knew there was at least one.
yeah. So with the moon challenge, I'm kind of I'm trying to formulate something here where we, instead of using shear pins to hold in the nose cone, we would use a servo motor with basically pins coming from the inside, and it would be holding under tension. Because I'm thinking a spring-loaded system throughout that would separate everything with the payload. So using a servo motor that has pins on the inside connected to it, that when that servo motor turns, those pins then are pulled inwards, releasing the spring, like the spring tension on the inside from basically the body of the rocket to the nose cone. And then that then would separate. But I didn't know if that was possible.
Allowed?
I have to use like shear pins.
I understand your concepts.
Yeah,
I
I'm
don't
kind of bouncing off the walls there.
I don't see any objections to it currently. Like, it doesn't violate any requirements. What I would do is, in your proposal that you write in 4 weeks, flush out as many details as you can out of that, but also propose an alternative, like a more, to me, that concept sounds a little more complicated than it needs to be. Okay. So propose also just an easier, shear pin, however else you're going to get it in or out, for example, right? And then based on the proposal feedback, we might kind of review it in a little more detail. And myself and Frank will give you feedback, a week later and say, hey, we don't like this concept, or we think it's a little unnecessary. Can you go to your second concept, for example? Does that make sense, Grant?
Yep. Thank you.
Yeah, I get it. You got to make sure on the release pins, there's all kinds of forces, up and down, left and right forces. You got to make sure that can release. So you have to put some poundage on it.
Yeah, I just feel like it's a nice concept. It's fancy, but it's a lot of moving parts, and there's a lot that could go wrong with that. So we'll need some more time to review that, and I kind of want to see a little more detail written out in a report. All right.
Yep. Sounds good.
Any other questions? Haley, come on, MIT. Tell us what you got.
They already got it. They don't want to say anything.
Nothing, Colin?
On UW.
I always got questions, but I just wanted to make sure everyone had space. My question is there any kind of limitation on the drone, like arm mechanic? Like, is there any kind of restrictions on the locking mechanism that's required? Like, how are you envisioning this locking taking place? Does it have to be a friction lock, or can it be just innate to the design of the drone? Like, is a spring that's holding it in tension considered locked? Or
Yeah, lock is fine. Mechanical is fine. Like, just a spring is fine. At least something there, right? Yeah. Like, even a spring, right? Like, if your deployment is spring loaded, and there's various types of springs, right? Like coil springs, or whatever type of spring you have. The spring itself may be considered a lock, right? Like, it requires more force to go this way than the other way, right? Like, once
Right.
it's deployed, that force may be sufficient to hold it in that position. But some springs may not, right? Some people may be deploying, and their deployments aren't as strong to hold it, so they're going to need some sort of hook or something to hold it in place.
You did a real good job, though, as an anchor.
My second question is there any kind of limitation on which way we mount the props? Like, can we mount the props so that they're pusher props instead of kind of in the pull prop orientation as a traditional drone would be?
Yeah, there's no restriction. So yeah, it's open to you guys. And again, that kind of depends on how you're folding everything up, right? It may be better to mount them as pushers instead of pullers.
Okay.
So we left that
Cool.
for you guys. Yeah.
Sweet. Thank you.
Thanks, Colin. Who else is on the RIT? You guys are new this year. Any questions?
Nope, I asked my question about the motor earlier. I think all of it's been answered.
Helen, you have any more questions?
None right
We can,
now.
we can also open it to outside of the challenge. Like, I mean, we specifically talked about challenge today, but if there's any other requirements or questions you got,
Well, I guess the the lander, uh, um, when deployed, it has to be 16 by 16 or more than 16 by 16, but it doesn't have to take contiguous, because when you show that drone, even though point to point it's 16 by 16, it's
Mhm.
not a total area. In between the rotors, there's empty spaces.
Mhm.
Yeah. So for the moon landers, even though it'll be 16 by 16 across at point to point, there's
Mhm.
there's nothing in between.
No, no, it's
Okay.
not. So then the reasoning behind that
Yeah.
is not so much the ground landing or even, you know, the drone flight stability. It's a little bit has to do with stability. Same thing with the moon lander, right? I mean, we want something stable when it's on the ground.
Okay.
If you're too narrow, right, the wind's going to blow. If your CG is too high, it's going to fall. So we want it
Right.
wide base and landing. But
Okay.
we also want to be able to see it at 2,000 feet. So when it comes out and everything's being deployed, right, you're all deploying at least 2,000, if not 2,500. We
Yeah.
want to kind of be able to see, you know, the size of, you know, and you think if you got an object or a body that's only, you know, 8 by inches square, you're probably not going to see that at 2,000 feet distance, right? But if you got these legs that are sticking out, you know, that are 16 by 16, you got a better chance of seeing that. And then even when
Well,
you're
but there's nothing between the legs.
no,
Yeah.
no. So your body of your lander, right, could just be a little 6-inch egg or a circle or a ball or whatever, right?
Yeah.
But the legs themselves will be, you know, 16 by 16 square,
All right.
but nothing between the legs. No.
Yeah. But then you got the parachute to help you see
Yeah,
the thing
yeah.
as it comes down. Yeah. Okay.
Yeah. And even just, you know, keep in mind like the coloring, right? Like maybe you want to paint your stuff bright orange, not,
Oh,
you
yeah.
know, just see it in the sky, not just to see it in the sky, but to see it on the ground too, right? When you go out into the field to recover, you know how it is out there, right? It's hard to see stuff sometimes. You could walk right by it and not even see it.
Yeah.
And that's why we want, you know, even for moon, you got to have a GPS on there and a camera. So those two things should help you recover as well as any visual aids you want to put on it.
Okay. We can put like an audio beeper as well to it.
Yeah, you could put additional electronics on it as well. If you guys want to put a, you know, sensor, work on some special payload that's sampling the air quality or something,
Okay.
by all means, go ahead.
Even though the student's supposed to design the stuff, is it okay if I put something like a sensor not related to the competition? Let's say if I want to sense CO2.
Yeah, because we're not going to be scoring that part. So if
Yeah,
you
yeah.
if you had something that was in addition to what the requirements were,
Yeah.
yeah, we're not going to score that.
Yeah.
So that's fine if you
Not a
did something and just
Yeah.
attached it or whatever. Just be
Yeah.
clear on that in the reports in launch weekend.
Yeah, okay, because I'm thinking like I may want to do some kind of sensing that since it's going up, we might as well do something about it and still keep the weight, because I think our weight will be kind of lower than usual. So
Mhm.
we can use the balance and let's do something about that.
Mhm.
Yeah.
That's fine. Yeah.
Okay, thanks. Yeah.
Just to confirm, for the drone, the 16 by 16 inch minimum is from like motor axle to motor axle essentially,
Yeah.
and not including the radius of the propeller.
Yeah.
Okay. Okay. Thank you.
Yeah, it's a trade-off. We know we kind of want small so we can get it in and get it all packed up, you know. But then once it comes out, we kind of want big for stability and visual cues, and then even recovery. We also want big. Those who've been to Bong, I think most of you have been there. You can imagine trying to find something 6-inch by 6-inch in that grass, right? You would rather want to find something 16 by 16, right? It's going to leave a bigger footprint. It's going to be easier to find.
It looks like the, on the rules here, deployed payload on the moon can be larger, should be larger than 16 by 16 square on
Yeah,
the
that's what I
landing
said.
here.
Yeah, that's what I said. It can be 16 or larger. So at least
Okay.
16 on everyone. If you guys want to go larger, and I don't think you will because you're all trying to figure out how to compact this as well. So I
Yeah,
figured
just a
most of
longer,
you-
just make a longer payload, that's all.
Thanks, Colin.
And with that, I'll stop recording, but